Hey, it's me, Miss Wesley, and I got a question for you. What is a butterfly's favorite subject in school? Mathematics. Today is when things get good. We're looking at limits packet page 11, and we've introduced limits, we've found them in tables, we've found them on graphs, we've seen types of functions where there are spots where limits don't exist, right, because of vertical asymptotes or maybe an oscillation occurring. And we've started to get into direct substitution. As I look at a page like 11 and I see these examples, I know that my best bet in number one is if I can directly substitute that -3 in for x in those two spots, that's going to be my quickest way. Not to think about what a graph would look like and think about the features of this function to say, okay, well, I'm going to plug in -3 to the top, but watch what I get. -9, 3 times -3 plus 9, I get a 0 up top. And then what do I get on the bottom? You plug in -3 in the bottom, you get 9 minus 9 is 0 on the bottom. This is a case that we haven't covered. I'm just going to put a question mark for the indeterminate form 0 over 0. We've actually said before that if you get a non-zero number over 0 when you do a plug-in, I don't know if you remember the easy answer. The easy answer, if I get like a 7 over 0, easy answer is limit does not exist. There's a vertical asymptote happening at that point. But if you get 0 over 0, that's not a red light, that's a green light. That means there actually is a solution to this problem. There's a hole at the point in question, but that doesn't mean there's not a limit. So here we go. We're going to start with some algebra today, so we don't have to think about all these graphs for a change. And it says dividing out technique. I like factoring and reducing. I'm looking at 1, 2, 3, and 4, and I bet if we tried these, there's going to be a way to factor and make something cancel, like I would if I were trying to find a hole in a rational function. So it says when you attempt to evaluate a limit by direct substitution, you encounter what I said was the indeterminate form. 0 over 0. That means there is going to be a solution. The numerator and denominator must just have a common factor, meaning in the graph there's got to be a hole, right? But the two sides are generally going to link up at a certain spot, so you could still, there's hope. You could still find a limit. After, we'll say factoring and dividing out, or I'll say and reducing the expression. So you're canceling off that common factor, then use direct substitution again. As soon as you're able to directly substitute, you should do it, right, to finish off the problem. So I see that's the case we're in number one. Might as well finish this one because we plug in -3 and we get 0 over 0. That means there's a solution. So I'm going to keep the limit notation here for a second. And I'm going to say it's still the limit as x approaches -3, but if I factor the top and factor the bottom, maybe that pesky common factor will be able to cancel and we can directly sub in. So I'm going to GCF up top, right? And we'll get 3 times x plus 3. We can factor a difference of squares on the bottom, x plus 3, x minus 3, and this was the culprit. Those two x plus 3's, I'm just so excited to cross them off because that's what was getting in the way of me being able to plug in the -3 and getting a real expression. As soon as I just have this over this, that's a green light for me to plug in -3. Let's just drop all other algebraic strategies and directly substitute this number into the remaining parts of the expression. No need for any limit notation here. As soon as you direct sub back in, I drop the word limit and I'll call it 3 over -3 minus 3. This is me plugging this in for x, and I got 3 over -6, so -1/2. And there's your solution, and like we mentioned before, it's kind of nice and convenient that we didn't have to think about what the graph looked like. We used algebra the whole way through and got this to a state where we could plug in a value. What we found was that at this x value, -3, there's a hole at the y value, -1/2. The hole happens here. And we talked about how, man, limits don't care what's happening at a certain point. They don't care that f of -3 is undefined. They're concerned with what's happening around it. So any limits question answer could be verified with a graph. I just quick put this function into Desmos, this original, and we care what was the limit as x approaches -3. You can trace on Desmos all around. It'll give you the y values that match with certain x values. If I go straight to -3 there, it gives me undefined. There's a hole there, but two people walking toward each other on that function would link up at that point. Can we skip down? I want to look at 3 and 4 and just make sure we're in the same case for these examples. Take a look at 3, see if you can factor, but let's make sure we should factor first. Well, will there be a solution? Before you start any one of these problems, especially if they're all mixed together, try a direct substitution. If you do an initial direct sub, you get, what do you get up top? 2 cubed, so 8 minus 8. You get a 0 up top, and you also get a 0 on the bottom. 2 minus 2 gives you 0. Here's your green light. Indeterminate form, 0 over 0 is being approached. That means there must be a solution. Let's try to factor out and cancel. So I'll leave the limit as x approaches 2. I will leave the bottom how it is, but we got to factor the top as a difference of cubes. I'm the kind of person that likes to sing when I do this. You don't have to sing if you don't want to, but you can listen to me. It's going to be cube root, same sign. So in the binomial, you'll have the cube root of x cubed, the cube root of 8, which is 2, and then the song or the pattern goes same sign. So inside there we can put a negative. Then in the trinomial parentheses, you're going to square it, put the x squared there, square it, we'll put the 4 there in the middle, multiply together and change the sign, best part of the song. So 2x, and the sign switches to plus. Well, that should have done the trick. Let's see, we can cancel, so we're dividing out top and bottom by x minus 2. That was the culprit. That was what was preventing us from just plugging in 2 to start with. So now drop the limit notation. Let's plug in a 2 to what's left over. So 2 squared plus 2 times 2 plus 4. You get 4 plus 4 plus 4. This function has a limit of 12 at that point. Again, there's going to be a hole, and let's look at the graph. Here's the graph. I went and typed it into Desmos. We care about the limit as x approaches 2. As I'm sliding up the function, I see the y values creeping up higher and higher and lower to get to exactly 12. At that spot, we have a hole. So if somebody asked me what's f of 2, I would say undefined, but we were able to find the limit by factoring. One more. I'd say pause the video, try 4 on your own, and then maybe tune back in, see if we get the same thing. That's up to you. But when you do factor, okay, so let's make sure factoring is going to do the trick. An initial direct sub would be 9 minus 3 times 3, so 9 minus 9 up top, you get a 0. Let's see what we get on the bottom. So 3 squared, 9, minus 5 times 3, so minus 15 plus 6 also gives you 0. 0 over 0 means there should be a solution. So let's try it. For the top to work out, because I see that x being negative, can we reorder it, make it negative 3x plus 9, and let's pull out a negative 3 instead of just a 3 as a GCF. So we've got limit as x approaches 3, negative 3, and then you get the x minus 3. That's going to set us up really nicely, pulling out that negative. On the bottom, I'm expecting an x minus 3 to result from the factoring, and if it goes with an x minus 2, I think we've got what we need, right? Let's cancel out the common factor. That'll just be a 1 over 1. And left over, you have negative 3. Over, let's do a direct sub now. We'll plug in 3 for x, so 3 minus 2. So this one's going to have a limit of negative 3. And we can always go back and check the graph, just like we did with the others, to make sure that looks good. So that's pretty cool. What else? I take a gander at 5 and 6, and it says rationalizing. And these are kind of funny to me, because first I want to know in number 5, is there going to be a solution? Like, can I be sure that I'm just not on a wild goose chase and I should just be putting DNE because I get something that's undefined? Well, not in this case. This one's like the ones above it, because if I plug in a 0 for x on top and bottom, I do get the indeterminate form. What is it? Square root of 0 plus 1, so 1 minus 1, a 0 up top and a 0 on the bottom. That means I have work to do. I have algebra I can do to determine this limit because we're approaching this indeterminate form, 0 over 0. So I'm going to recopy the limit notation. When I show my work for these problems, you're going to see sometimes it gets kind of cumbersome to just recopy that limit notation time after time after time. I always do it because I'm the teacher and I want to be careful. The AP test, the scorers, they want to see you do it. They want to see that limit notation copied. And like I said, once you get down to this spot in green here where you've already done your plug-in, that's when it's okay to get rid of it. So I'll try to get in the good habit. Well, what am I going to do to this one? We're going to use the conjugate. And that's why I said this one was kind of curious, because in our practice so far, the times we wanted to get rid of radicals were when we wanted to get them out of a denominator. Well, here in 5 and 6, we're actually going to rationalize the numerator. We're going to find the spot where there's some troublesome rational expression, and let's just squeeze in. I didn't leave myself a lot of room here, but let's squeeze in the conjugate on top and bottom. That's what I want to do. I'll just slide this down and put it on bottom as well. So the conjugate is not going to change this first sign. Square root of x plus 1 stays intact, and the 1 stays what it is, but we're going to change this sign in the middle. Conjugates are awesome. They simplify things. They make radicals completely vanish, and I think it's really going to do the trick here to be able to hopefully eventually plug in a 0. So let's put that conjugate on the bottom too. Square root of x plus 1 plus 1. Let's use, I'll just remind myself that I'm using conjugate, the conjugate. Okay, now to simplify, let's see if we can FOIL the two expressions together that we just wrote, and I'm claiming lots of terms will drop out. So first times first, square root of x plus 1 times exactly itself is just going to give you what was inside of that radical. There is no need to write the inner and outer terms anytime you're multiplying conjugates together because you'll have positive this root and negative that root. But I do have a final term. The final term is going to be negative 1 times positive 1, so minus a 1. Now what's funny is there's two reasons I am not going to distribute through on the bottom and get rid of the parentheses. I'm actually going to leave it like this. It's not just because I'm being lazy, it's because think of what you want to happen. I mean, what was the whole problem? What was the major problem with being able to plug into 0 in the original? It was this denominator. It was this x. If there's some way to get rid of this x, we want to do it. And if we're hoping things will cancel, and we're hoping this will cancel, it's better to leave it out front, factored out, rather than distribute it in. That's the major reason. Does that happen? Well, what do we have up top? We have the limit as x approaches 0. Have you already figured this out? X plus 1 minus 1. Perfect. I'm glad we left this x outside of parentheses because now it gets to go away. And I don't have to do any more algebra. I can go straight to a direct substitution, dropping the limit notation, plugging in the 0. And I get 1 over square root of 1 plus 1. For some reason, a half is a common answer on this page. Go figure. You get a half as your limit. Can be checked with a graph. Feel free to try 6 on your own. See if a quick conjugate, I think this one's going to be very quick actually, and then you could tube back in. A direct sub actually is going to give you square root of 4 minus 2. So 2 minus 2 gives you 0 up top. 4 minus 4 gives you 0 on the bottom. Perfect time to use a conjugate. Okay, so we'll use the conjugate of the radical expression. Square root of x plus 2. Square root of x plus 2. Let's see if our simplifying goes okay. So we want the limit as x approaches, I think it's 4. We will yes FOIL up top so that it simplifies. That's why we use the conjugate in the first place. So first term x, inner and outer cancel, plus 2 of these roots minus 2 of those roots. Last is going to be minus 4. Can you notice right now that this is a great thing because you have that on the bottom too? Well, absolutely. Let's not FOIL this. Let's have x minus 4, square root of x plus 2, and get rid of what we wanted to go away. No more limit notation needed. We've got 1 over the square root of 4 plus 2. So 1 over didn't get a half this time. 1 over 2 plus 2, we get a quarter. Okay, we'll see a little bit more algebra on the other page. In 7 and 8, if you go back and try these, you want to simplify first. If you try 7 on your own, my advice is it's hard to do a direct sub at first. You get 2 undefined expressions. Combine these together as one, it'll be easier to get your limit. I wanted to try 8 with you. At least talk about strategies to start number 8 and then have you take it from there. Direct sub initially of a 0 would give you the indeterminate form 0 over 0. So that means we have some algebra to do. We want to combine these two top fractions together. Right now this is a complex fraction and we want to make it less complex. The first fraction, if we want this common denominator of 3 times x plus 3, first fraction needs a 3 on top and bottom, so I'll just put that up top. The second fraction needs an x plus 3 on top and bottom. So that's kind of what it'll look like for starters, and it's all divided by x. With my apologies for speeding this up a little bit, and we'll have much more of a chance to practice with this in the coming days, watch what happens. Up here, you just have a negative x when you simplify that over 3 times x plus 3. And dividing by this x is the same thing as swinging it up and multiplying by 1 over x. We can cancel those, and that should do the trick. So not showing every little step along the way, but being confident in my algebra here, I get something I can directly sub into. Negative 1 over 3 times 0 plus 3, I get negative 1/9. All right, if you thought that was fun, we've got some more good stuff in the coming days. Hope you enjoy the rest of your day, and cheers with a Dr. Pepper. Whoops, see you later.